About the weight lattice and the Brouard decomposition, which is the last argument before we compute this strange Poisson bracket. Okay, so we know what is Borel. So we take so an element of H star we call a weight, and what are the fundamental weights? So I want, no, there is one thing I want to say before this. I'm sorry, I'm not going in a very organized order. Let's say what's the fundamental weight before. So we know that the roots are elements of H star. And what do we call a fundamental weight? So, omega is the fundamental weight. If it has this property, omega I, 2 times so if you take this this number, which is okay, you remember that if we have a root where this is an integer, right? This is a Cartan integer. You take an element of H star. You can compute the Cartan-Killing form because we know it is extended to the dual. You divide by the length of the root, which, well, whatever. And this is delta ij. So if you get this element that behaves like this, it's called a fundamental weight. This is just a definition. No? You don't agree?
The fundamental weight is a linear combination of these elements with negative coefficients. A fundamental weight is an element.
No, it depends on your definition, though. I mean, it defines it like this.
Okay.
I always seen the. Wait. No, wait. I always. Sì, è quello lì. No, you're the dominant weight. Okay, let me. Okay. If one say like this, one doesn't understand why on the hell one should worry about such a thing, of course. Because I say, okay, you have told me this element of H star, what do I do with it? Because it makes no sense.
You can define it as omega E of Hj equal to delta Ij. I think it is simpler to see that.
Vabbè, Nico.
It is an element.
No, vabbè, ho capito. I know all the properties. Yes, she says.
You are introducing it as an element in H star. If you define it on a basis of H, I think it is.
No. Let's do it as you say. So she says the following. So the alpha j. Okay. Let me write this because it's important. What Nicoletta says is very right. She says that. If alpha is simple, we know that there is H associated with simple root, which we call it Hi. Is the H associated, we know that there is this thing I said at the beginning, there is an SL2 sitting in there, blah, blah, blah. Now, she says correctly that the fundamental weight has the property, and it's very easy to see in a moment. Fundamental weight has the property that omega I Hj is equal to delta Ij. Now, how is this related to that? It's related because the Cartan killing establishes correspondence between H and H star, in which a simple alpha I is associated to oh wait, no, è qui un casino, because
I was just suggesting to give this definition, but if you
no.
need the other one, okay, that's all.
No, but one would like to know what they're equivalent, right? So no, because otherwise it's really okay. If you have the Cartan killing, it establishes this correspondence, right? So if you have an element, see, it's very unfortunate. If you have an element here, there is clearly correspondence with an element which I call H tilde alpha here. Now this H tilde alpha, how is it related with this? So this is not equal, unfortunately. This is not equal to H alpha I, unfortunately, but it's equal to, so Nicoletta, help me if I'm wrong, it should be H tilde alpha I 2 times, am I right? So, the Cartan killing establishes a one-to-one correspondence between H star and H, except that this H alpha I is chosen to make the SL2. So we are forced, if we want to have the SL2 rules, to renormalize. And the factor we have to renormalize is this. Unfortunate, because see, you want HI, X alpha I, Y alpha I to be the same as SL2C. You want this. And if you don't do this normalization, you will not find SL2. You will find something that looks almost like SL2, but doesn't have the right coefficients. Okay? And so, if you look at this equation, it is the same as this equation. Once you do the normalization, right? Because alpha j corresponds to H tilde, and this is to, so this thing is all corresponding to Hj, right? So it's the same. This is one of these little stupid things that messes up, because if you forget this coefficient, it becomes a tragedy in the theory. Now, this still leaves open the question, why would we ever care about the fundamental weights, right? It's a long story. Why do we care about fundamental weights? Because they are the building blocks for the representations. So, I guess that here is no need. So for a choice of an element in H star, you can build a representation. Maybe not finite dimensionally. Any element corresponds to the representation. If you care about the finite dimensional representations, you need to choose some certain elements of H star, not all of them. Precisely those that correspond. So for each choice, I try to say, but it's kind of a tragedy because the theory is very long to explain. So, finite dimensional representation of G simple over C. They one-to-one correspond to dominant integral weights. that is, this means elements, say lambda in, no, lambda used for a bit, but let's call lambda in H star, that are written like this, M1 omega 1 plus Mn omega n. Right? This is what we want to say. Positive, integral,
The MIs are non-negative.
Yes.
Yes, an integral also.
But
Dominant
non-negative.
Yes, dominant means non-negative.
You should write.
Ah, yes, I should write. So, Mi, but the word dominant means positive integral the integers. So, I thought I wrote the wrong thing because you jumped at me right away. Okay. So it is a highly non-trivial point, but this is why he cares about defining it. Evidently, he will need. Okay, so this is.
Rita, can I ask you for a plan?
What?
A plan of what we are going to do?
I don't know the plan.
No, I mean.
I've been
is
hired.
your plan?
I've been hired for the first chapter only.
Okay, so in this chapter,
I'm almost finished.
okay, but you are, at the moment you are reviewing some lead theory.
Yes, I don't know why though.
Okay.
I have no idea why I'm doing this. Because Fabrizio knows everything.
But at least you have
But,
a purpose because you said something about Poisson structures.
Yes,
To go
yes.
back to Poisson.
Yes, we go to Poisson. Hopefully today, I don't know.
Okay,
We'll see.
in order to do that, you need some.
No, weight we don't need. We need lead theory. Yes, we need lead theory, but not weights we could have skipped. Okay.
No, that's
But weights it took only 5 minutes. Now there is something which we should not skip, which is this. So this ends my discussion of weights. I will come. No, there is something I wanted to say, but maybe not now. So I forgot to say something at this point, which I say now, because I need it for the. Let's see how much I need, because maybe I don't say it at all. I decided not to say it. I will say it later. Great. Okay, so let's continue with the fundamental weights, okay? So he gives this definition, which he says it's very important, and he uses it to compute something, okay? So he says, let us consider x in porca miseria, we need it now. I'm sorry. We need this thing. We need the big cell of G. So we still need one piece more of information. So G sits here with tangent space, this. Each of these subalgebras have corresponding subgroups. Right? So there is, okay. The Lie algebra is the sum of three things. Each of these subalgebras have a corresponding Lie subgroup. Now, if you take the product of these things, now the product of these three groups is not a group. If you take the product, so I'm saying that you just take products of one element in here, an element here, and an element in here. So this is inside G, except that this object is very large inside G. Because if you compute, it will have the same tangent space as this. So this will be its tangent space. So we're looking at the product of groups as a submanifold structure. So we have a submanifold sitting inside the manifold with the same tangent space. So it is open. And we care about this open. It's called the big cell. Because it's big. What you leave out is very small. Very, very small. Now I know it's hateful when one says these things.
Sorry, why the tangent space should be?
Because it's very simple to establish. Because certainly n minus is inside here, right? And it has this tangent space. H is inside here, it has this, n plus is this. So for sure, the tangent space must contain all of this. And well, this is the most it can contain, because this is all G and this sits inside G. So it is the tangent space. Now, when I say it's big, it's Zariski open, okay? So it means that we know what this means, Zariski open, do we? Right? So what is leaving out is just the zeros of some polynomial. Now you may wonder what are the polynomials that are left out. That would be a very good question. And in fact, in the calculation that we're going to make now, it will turn out that we know what is this left out. We're going to make a little calculation. Okay? They're not happy. Yes, Stephen is not.
The pedantic point. But how do you know that the complex Swedish has an algebraic structure?
No, it's absolutely very good question. But let me no. But let me be extremely naive. Okay. So this group is a matrix group. It lives inside some matrices, right? And so this opening will be defined as zero polynomials in this matrix elements. Okay. Very naive. This is accurate, right? But it's true that every complex group through the Gaga analytic has a unique algebraic group structure sitting on it, but we don't care. Okay? So it can be done at a more high level. Cosa succede?
I was a little confused by the fact that you spoke of Zariski.
Zariski.
I know,
but we're going to see example now.
Yes, but the structure we are looking at now.
No, it's complex analytic.
Okay.
Not called algebraic, never, because all of this theory is using algebraic groups as device, but it's not algebraic group, from what I understand. But then Fabrizio, you will have to follow this book, because I follow the book. So, no? No, ma dai però. No, scusa però. No, I'm doing all this thing. Okay, so he does this thing which, okay. So if you take an element in here, you can express it as product of x minus x0 and x plus, and you can express it in a unique way. This is not trivial to show, okay? Because you can, yeah, I mean, I don't see why it should be true. You should know something, right? In order to express this as a unique way, you should prove that this is, which we know it is true, but, so this fact is true, but it requires some effort to prove. It's not evident. Okay. Now, he defines the following. So this is definition. So we take x in, so he calls this thing, I'm sorry, what do I want? I'm confused. I've written two different things. Right. So let's call all of this G0. So this is the open in G. And let us take an element in G0. And let us take a fundamental weight, which we know it is linked to representation in some way which we have not understood. And then we define the following. X0, I explain, omega I. So x is written in a unique way as x minus x0 and x plus. So we take this x0 in H, and we do this by definition. When he writes like this, it means exponential of omega I H, where H is such that x0 is the exponential of H. And this is a number, okay? So this is an element, it's a complex number. This is very, what can I say? It is very, very dark, very opaque in the definition. But then he makes this interesting claim saying that this is the principal minus. But we're going to do this because this calculation I could make. So he says that, example, if G is SL and C, delta I is the principal I minus minor, is the determinant, okay? Is the determinant of the principal I times I minor. And in fact, you could tell it right away by looking at the definition. No, it's not immediate. But let us compute this. I want to, before we do this, I want to get the attention of my friends of Chevalier groups. You remember that at some point in the proof of this result, the principal minus came into the play, right? You remember we're looking at these determinants. So it's really linked to this decomposition. So let us compute. I made a calculation. It doesn't need a calculation. So he makes an observation, which is let me say the exact phrase because, so he says, this is a regular function. He speaks about a regular function defined on G0. I think by regular functions he means an algebraic function. And he sort of says that if you have an algebraic function or as a risky open, you can extend it uniquely to the whole G. So he makes this claim. So he uses the fact that you have a complex analytic structure. There is an algebraic structure corresponding to it. He's using it implicitly. But Fabrizio, whatever book you use, you better use all of this because it took me a long time to work these things to understand. So,
Anche se non ti serve.
no, tu devi usare. You're going to use them even if you... Okay, so let us make the calculation for I made the calculation for SL2, for SL3, and then I became convinced for SLN. Right? Don't laugh because if I leave yourself in your room with this calculation, I'm not sure. No, Fabrizio, I'm sure, but all of you guys that are laughing, I'm not sure. No, because it's so funny, but it couldn't make the calculation. Okay, so this take, so for SL2, x0 the most general, we worked it out before, is e to the h, e to the minus h, right? This was the general expression. Now, what if we take, so first of all, what is omega in this case? Well, for SL2 there is just one fundamental weight, which corresponds to half the root. What does omega 1 do? Does? We have to know. So, this goes from omega 1 of h minus h. So this will give you h, right? Right. So this is the fundamental weight for SL2. I erased it. What is h? So omega 1, this is h1. So this must give 1, which is the delta ij. So if you apply it to h minus h, it is h. All right. We'll laugh less later. Now, what is so the claim is that delta I is the principal I times I minor of x in G0. This is the claim. So we need to write x in G0, but we are very happy about this. So x in G0, it has the following. So it is a product of an element of n minus h and n plus. N minus h and n plus we know extremely well, because n minus is the one parameter subgroups of this type, so it is 1 u1 times you remember that the negative roots would give rise to this one parameter. Well, there could be many one parameter, but where in SL2 there is just one. There is one root and one parameter. And if you make this little bit of calculation, this is t, ut, big T, utv plus t minus 1. This is the generic element. Now, what is the definition? Definition says that delta Ix is equal to exponential of omega IH. Omega IH, omega 1H is H. This is e to the h, which is t. Right? So this is this is x0, right? This is my x0. So we're very happy. This is the principal 1, 1 minor. So this was the silly case. Now let's do little harder case. SL2.
SL3.
Yes, SL3. So the so I'll do it here. And it will be, now if one knows this calculation, realizes that this is really the same, but let's do it now, because it's less trivial. Okay, so we have to know what are the fundamental weights, okay? Because here in the case of SL2, the weight is very simple. It's just that. So what is for SLNC? What are the fundamental weights? Do you remember what are the fundamental weights? There will be a sum of the. Okay, so omega I is. How do I dream of it? I look at it in a book because I don't have the energy to compute. So, what is lambda for me? Lambda I?
Rita, is it true that the principal minor of x is the same as the principal minor of x0?
Ah, no, I know, but here,
Because
no, wait.
you have this element in n which are important.
No. Let me explain what I understand. Certainly, if you take an x in G0, this is the principal minor, right?
Yes.
This is the calculation. So this function will give you for all the elements of G0, this big Zariski, it will give you back the principal minor. So let us look at the regular function of the whole group that takes a matrix and gives you back the principal minor. These two functions coincide on the big cell, they have to be the same.
No, I mean,
This is the
if you
argument.
take x in G0, I guess.
G0?
Yes.
Mhm.
I guess
Yes,
the principal
yes.
minors of x are the same as the principal minors
Is a
of
question?
x0.
Is a question?
Yeah, it's
We're going to
rather
show.
an observation.
We're going to show. I make the calculation.
But it's triggered because
I'm happy
these
to say that.
unipotent matrices.
Yes,
So you
yes,
multiply the principal
absolutely,
minor.
yes.
So
It is true what you say,
So you
absolutely.
don't
It's
need
a
to
trick.
do the computation.
We don't need. ESS is the same. But maybe I work out the principal minor because the fundamental weight. It's absolutely true what you say. It's not. I'm not questioning. But let me do things in an order, okay? So I have no doubts that you could do the calculation. Even you do it without the calculation. Even back. No, at some point you have to realize that omega is connected with the principal minors. So you need to know what omega is. You cannot dream of it. You have to make this little thing.
No, I was just saying that you don't need to do the product. We knew a priori that the
Okay,
principal minor was
absolutely,
E.
yes, because it says, look at the principal minor of this, yes.
Yes.
But omega 1 you need to know what it does.
Yes.
Okay, so let me go back to the fundamental weight because so I'm claiming the fundamental weight as this aspect. So where omega I of A1 n is equal to AI. Facciamo il calcolo però Fabrizio, dai, no, perché sennò, cioè, qui è un disastro. So, fundamental weight, it does this. Why is it working? Now if you try, so if you try it out, it works. So if you try to apply it to the HIs, it will give you the correct, you don't agree with this, I mean it's, though I checked it out in Humphreys, so this is Varadarajan's book giving the fundamental weights for SLM. Now in Humphreys it will give you in terms of the roots, so it is different because of that. So I tried the one of Humphreys and I just couldn't prove they are the same, but they have to be the same, so I don't know. There's some calculations, but now, so this for SL3, omega 1 is still lambda 1, omega 2 is lambda 1 plus lambda 2, and this is it. We have two fundamental weights. Now, let's try the calculation. So if we say, so delta 1 it will be the same, obviously. Now, delta 2 of an element x, so T1, T2, T3, sorry. So if we take an element x, so this will be, so x will be written as something like 1, and then you have T1, T2, T3, and then you have 1, 1, 1, and then the stars here. So this is how you decompose an element. This is x minus, x0, and x plus. So this will be the exponential of lambda 1 plus lambda 2 applied to T1, T2, T3. Okay? So this will be the exponential, no, sorry, not T1, of H1, H2, H3, where you have that e to the H1, e to the H2, e to the H3 is equal to T1, T2, T3. So you want an element H that exponential gives you the one downstairs. So this will be H1 plus H2. So this will be exponential e to the H1 plus H2. So it will be T1, T2. So this will give you the principal minor. Now, Marta correctly says, I don't believe it, and I also don't believe it. Fabrizio, you are very right. But the calculation is really immediate. So if you try to make this calculation, so if you try to compute this and check what is the principal minor, it's really the same, right? And the reason, if you think of it, is that it's the same calculation as before, right? If you multiply these matrices, you will find out that the principal minor is really T1 times T2. I mean, if you can do it, it's like whatever. I mean, it comes out, so it will come out something like this, okay? T1, and then you have T1V, U T1, and then you have U T1V plus T2, whatever it is here. And when you do the product, and no, it's T2 here, right? What is T1? So T1 is here, and then how can I make a mistake on this very stupid thing? Oh, yeah, no, it's coming, of course. So it is T1 U T1V plus T2 minus U T1 T1V, and so this was, so it is T1 T2. It's really the same as you said. And now you understand that it's really, if you do for SLN, it's the same. Because if your omega I are the sum up to, so this will correspond to H1 plus HI, and then will be T1 times PI, right? That will be the principal minors. So it is the calculation that I've made. Now, I knew I couldn't do. Oh no, I have time to. Right. So he decides to do a slightly different thing. So are we sort of happy with this calculation? But you have an idea of the plan, because I agree with Nicoletta. Why do we need all of this? It's not clear, right? No.
No.
Okay.
When shall we meet the cluster algebra for the first time? Do we know that?
No, I want
It depends.
I believe in the regular functions on the
Yes, but when? Not when. So when math is in math's first time.
Yes.
You will speak about the cluster.
No, it depends on okay, sorry. But you have to be patient. Sorry.
In the segment of Chevalier groups, we spoke about Chevalier groups only after so much time.
Okay.
We needed all representation theory, do you remember?
Right.
There were to do all of this craziness about the integral form of universal developing algebra.
At least the word.
The word.
Cluster.
No, I want to.
Mentioning.
No, I want to. I wanted to spend a second to realize that, you see, all elements that belong to this G0 share this nice property that all the principal minors are invertible, you see? And that characterizes them. So this is really the Zariski open type of argument, right? You see? Yes, this is what I wanted to say. That if you try to write an element belonging to this thing, this G0, which is this, certainly all the elements that belong to that have the property of the invertible principal minors. But what I believe is that if you know the principal minors are invertible, you can always put them in that form. I've not done the calculation, but I think you can. Right, Fabrizio? You are very smart. Can you figure out how to do it? It's not hard, I think.
I'm sorry.
So if you take the principal minors and you claim, if you ask they're invertible, then you can always write an element with that decomposition. I think this is true. Certainly for SL2 it is true. For SL2 is immediate, right? Because if you get invertibility, well, it's not immediate. It requires a little calculation. If you require T to be invertible, then you can always write this splitting. Suppose that you have this A, B, C, D, and you say, okay, this is non-zero, then you can write this decomposition. So this I have done. It's very simple to do. It's just a little calculation. I think that if you have all the minors invertible, I think you can reproduce the same calculation. It's, I think it's like solving a system of equation that...
I guess it's just Gauss algorithm.
Right, it seems to be not hard.
Yeah. Because if you have the principal minors non-zero, it means that
yes, you can.
You obtain doing
or possibly
operations on rows, you obtain a diagonal matrix. So,
I mean, yeah, there is some argument. For me, it's clear that there is this argument, even if I cannot do it. I'm not technically very smart. But this gives you an idea that really saying it is Zariski open, it has this meaning.
So it's like on the left side you do all the row operations, and the right side you do all the calculus. That way you have two sides. Because that factorization has a matrix on the left.
Mm-hmm.
yeah, multiplying by those two matrices, you can obtain a monomial matrix. And the only monomial matrices who have non-zero principal minors are the diagonal matrices.
For me, intuitively, it's clear. I should write the argument, but this all I wanted to say is this is abstract condition, or Zariski open. It assumes a very concrete meaning by saying principal minors are invertible. And trust me, if you have a different group, not SLN, it is the same condition, except that instead of picking the principal minors, what were we picking? We were picking this. You remember there was this. We were taking the, oh God, what was it? We're taking the root elements, right? I forget what we were doing. I remember we were taking a wedge product of something, and so would come out the determinants. I forget. It is very similar. So it's reproducible. I remember that the argument this time was lacking, and you helped us, Fabrizio, but it was so much time ago. I forget. Okay, so now the madness is pushed forward, so it's becoming more complicated. So it says, so it gives the definition of